Today, we're going to pull back the curtain on an incredible chemical journey. We're talking about how we turn a simple reddish-brown rock into the essential building block for one of the most common metals on Earth, aluminum. It's a wild process involving immense heat, intense pressure, and some seriously precise chemistry. I mean, think about it. You see it everywhere, in your soda cans, in airplanes, even in the phone you might be holding. But aluminum doesn't just, pop out of the earth ready to go. No way. It starts as a rock, and it has to go through this massive transformation inside a huge chemical refinery. So, where does this all kick off? Well, the journey starts with a raw ore called bauxite. This is our starting material, our reddish rock, and it gets shipped off to a giant industrial plant, a refinery. This is where all the magic and all the heavy-duty chemistry is about to happen. Okay, before we dive into the nitty-gritty, let's talk about what we're actually trying to make here. The end goal, the whole point of this journey, is something called alumina. It's this super fine white powder. This entire super complex process we're about to walk through, it's all designed to produce just this one thing, because this is the essential ingredient you need to eventually make the aluminum metal we all know. All right, so we've got our rock. How in the world do we get that pure white powder out of it? Well, it all kicks off with stage 1, digestion. And you can pretty much think of it as giving the rock a very, very hot chemical bath. On paper, it sounds kind of simple, right? First, you grind the bauxite ore down into a powder. You do that to get as much surface area as possible. Then, you mix that powder into a really powerful chemical solution. And finally, you cook the whole thing under some serious heat and pressure to get the chemical reaction we're looking for. So what's the magic ingredient in that chemical bath? Well, it's this stuff, caustic soda. It's a super strong solution, and it has one very specific job. It's designed to dissolve the valuable alumina right out of the rock, while leaving most of the other junk, the other minerals, behind. It's like a highly selective chemical key, unlocking only what we want. And once that digestion stage is done, what you're left with is, well, it's a slurry. It's this thick, soupy, muddy-looking mixture. And the really cool part is, in this chemical soup, all of our valuable alumina is now completely dissolved in the liquid, but all the impurities are still solids, just kind of floating around in there. Okay, so we've got a bit of a situation. Our good stuff, the alumina, is in the liquid, but it's all mixed up with this leftover gunk. So stage 2 is all about the big cleanup. We have to separate the good from the bad, and we do that through clarification and filtration. But that's the million-dollar question, right? How exactly do you do that? How do you perfectly strain out all those tiny, unwanted solid particles from this valuable chemical soup you've just created? And this is where we have a major fork in the road. The separation creates two very different things. On one side, you've got the good stuff, the valuable sodium aluminate solution. This liquid holds all our precious alumina, and it gets to move on to the next stage. And on the other side, well, you've got the waste product, a residue known as red mud, which has to be washed and then stored very carefully. Now let's talk about this red mud for a second, because it's a really big deal. It's the main residue from the Bayer process, and it's loaded with leftover caustic chemicals and iron compounds. That iron is what gives the mud its signature red color, and it also represents a pretty significant environmental challenge for every single refinery out there. All right, we've cleaned up our liquid. Now for the really clever part, stage 3, precipitation. This is where we basically reverse what we just did. We have to somehow convince the alumina that's dissolved in the liquid to turn back into a solid. Only this time we want it in a super pure form. This process is called crystallization, and honestly the best way to think about it is like making rock candy. You start by cooling the hot solution down. Then you seed it. You literally add in these tiny pre-existing pure crystals. Those little seeds act as a starting point, and then brand new pure alumina crystals start to form and grow all around them. It's pretty cool. And these beautiful little crystals that form, that's our stuff. That's hydrate. It's pure aluminum hydroxide. This is the very substance we've been working so hard this whole time to isolate. We finally separated it from all those impurities that were in the original bauxite rock. We've got our pure crystals, but hold on, we are not done yet. It's time for the grand finale, the fiery finish. That's stage 4, calcination. This is the last purification step that's going to get us to our ultimate goal. And calcination is exactly what it sounds like. It is all about crazy intense heat. Those hydrate crystals get roasted in these enormous rotating kilns at temperatures over 1,000 degrees Celsius. That intense heat literally drives off the water molecules that are bonded to the hydrate, and what's left behind? Just one thing: that pure, white aluminum powder we were aiming for from the very beginning. So after all that grinding, cooking, filtering, and roasting, you have to ask why? Why go through this insane multi-stage chemical marathon? It all boils down to one single, incredibly important word: purity. This entire process is designed for a single reason: to take a jumbled up rock and refine it into a product that is more than 99.5% pure. And that level of purity is absolutely crucial because any little bit of impurity left over would weaken the final aluminum metal, making it brittle and totally unreliable. You know, when you're running one of these massive refineries in the real world, your success basically comes down to a few key numbers on your scorecard. First, there's yield. How much alumina did you actually manage to get out of the ore? Second is efficiency. How well did you use your resources, like your caustic soda and your water? And finally, a huge one: energy. Just how much power did this whole thing consume? And that really brings us to the big final question we have to grapple with. The Bayer process is, without a doubt, an engineering marvel that literally powers our modern world. But the challenge for the future is this: how do we balance our constant need for aluminum against the true cost of its massive energy consumption and, of course, the environmental legacy of all that red mud it leaves behind?